Okay, this is HL Paper 2 question 2 and SL Paper 2 question 5. It's all about electricity. And initially we're dealing with some static electricity. So it says, by considering the distribution of charge on the sphere, state and explain whether the tension in the string holding the charged particle will be less than, equal to, or greater than the weight of the particle. Alright, so it tells you that it's a metallic sphere, and we know that that means that the electrons are able to move. The protons will still be fixed, but if we bring a positively charged particle nearby, the negatively charged electrons will come towards the top of the sphere. That means that there's going to be an attractive force between the positively charged particle and the negative charge at the top of the metallic sphere. Because of that, there's an additional force on the positively charged particle, which therefore will add to the weight. So the things that you're looking for is that the force is going to be greater because negative charges form at the top. Of the sphere, and therefore there's an attractive force between the particle and the sphere. Right, over the page it gets a little bit more complex. So this symbol here means that it's earthed or grounded, which essentially means that electrons are able to flow to or from this sphere as they like. So on each diagram A, B and C, draw the distribution of charge on the sphere. Well, if we bring a positively charged particle close to the sphere, that's going to attract additional electrons up towards the top. Okay, kind of similar to what we had before, except there's probably going to be more electrons that have come from Earth. Now, when we remove the Earth, that means that those electrons are still going to stay on the sphere. Nothing has changed that, and in fact, they're still going to be attracted towards this positively charged particle. It's the wording of the question. It says the Earth is then removed. Okay. Finally, the charged particle is taken away, so that's again sequential. It's afterwards. Well, once that happens, there's nothing to attract the negative charges up to the top. They are excess negative charges that will then distribute themselves evenly around the sphere. They're going to repel each other, so they'll distribute as evenly as possible. It then says, explain why work has to be done on the charged particle to move it away from the sphere. So in order to move this way, and the mark scheme was looking for, it's pretty simple actually. It says there is an attractive force and therefore work has to be done. Bit odd because it's said in the question, but there you go. Alternatively, you could have talked about the fact that there's a negative potential energy and therefore positive work must be done to remove the particle further away. Over the page, we get into some circuits rather than static electricity, and you start off by having to define EMF. Now, this is a notorious definition question. We all know it as the voltage of the cell or the supply, but the actual definition needs to be work done per unit charge, fine so far, in moving an electron, in moving a unit charge completely around the circuit. Okay, that is the IB definition that you must learn for this one. It says in the circuit below, the battery has an EMF of 12 and an internal resistance of 5. I'm actually going to draw that in as a little internal resistor here to remind me later on. Calculate the total resistance of the circuit. Right. So we know that in order to add up resistance in series, you simply add them together, and in parallel, you add the reciprocals. So we're going to start off by doing this bit here. 60 ohms plus 30 ohms gives me 90. Same for this one here, 30 ohms plus 60 ohms gives me 90. Now those are on parallel branches, so to add those in parallel, we do 1 over R1 plus 1 over R2. That's 1 over 90 plus 1 over 90, 2 over 90, which is the same as 1 over 45. Don't forget that you've done the reciprocal of the total resistance, so that gives us a total resistance of 45 ohms so far, plus the 5 ohm internal resistance means that we end up with 50 ohms as a total. Okay? It then says calculate the current within the internal resistance. Well, the current that's going to be drawn away, so the current will be moving away from the positive side here, will be the same as the current entering the cell and through my internal resistor here. It's essentially the current that's going through the cell. So you need to do that, you just do the EMF divided by the total resistance of the circuit. That in this case is 12 over 50, which gives me a grand total of 0.24, and of course the units are amps. Right, it then says to calculate the total power that's dissipated in the circuit. The easiest way to think about this one is P equals IV. Well, if it's total power, then we should deal with the current that's leaving the cell, and we've just calculated that as 0.24. And the voltage is the total voltage that's supplied, which is the EMF, which is 12. That gives us 2.9, and again the units this time are watts. This next part asks you to find the potential difference between points X and Y. So if we look back at the diagram, there's two ways to do this. You can either go this way or this way to get between these 2 points. Now, earlier on, we calculated that the current leaving the cell, so on this section, is 0.24 amps. We know that that current is then going to split down these two branches evenly because they've both got the same resistor. So, same total resistance. That means the current going through here is 0.12 amps, and the current going down this one is 0.12 amps before they recombine. So, if we think about going from X to Y in a clockwise manner, well, 30 times 0.12 gives us the voltage that's lost across this 30 ohm resistor. And that gives us a voltage of 3.6 volts. Similarly, if we do 0.12 times 60, that gives us a voltage lost of 7.2 volts. Because one is a gain and one is a loss, that means that the total potential difference between X and Y ends up being negative 3.6. Or just because it's a potential difference, you're allowed to just say 3.6. So voltage of the 30 ohm is 3.6 volts. Voltage of the 60 ohm is 7.2 volts. And the difference between those two, so X to Y, is 3.6. The last part says a real or non-ideal voltmeter is connected across points X and Y. What would this do to the value of the voltmeter? Between X and Y at this point, because there's no connection, there is an infinite resistance. However, as soon as I connect a voltmeter, a non-ideal voltmeter allows some current through because its resistance cannot be infinite. So some current flows through. From X to Y. When a voltmeter is added, as it does not have an infinite resistance. Which it did before. And that would get you the 2 marks for that question.